Okay, so let's do a maybe it won't be any better. So let's do an example where we have two walls and a third of the way along we apply a torque this way of 2,000 Newton meters, and then a third of the way from the other side we have another torque in the same direction of 4,000 Newton meters. What are the reaction loads at the walls? Well, the first thing we have to do is figure out, so we don't know that it's statically indeterminate yet. So let's do the statics and figure out whether we're going to need extra equations or not. I'm just going to choose positive x directions for the torques at the walls. So I'll call this TA, TB, and then this one, and this one. We don't have any forces. We don't have anything that'll produce moments about the z-axis. So I'm just going to use rotational Newton's second law about the x-axis. And it says TA minus 2,000 minus 4,000 plus TB is equal to 0. And so our first statics equation says TA plus TB is equal to 6,000. That's one equation for two unknowns. So that means it's statically indeterminate and we need a constraint equation. So we're going to need a constraint equation that relates to deformation. Okay, so I'm going to use angle of twist. And to do that, I need to figure out the internal torques at every point. So we're going to make 3 cuts. That's a good question. Are we going to need to know? I think the answer is it would come out the same as long as the proportions are the same in this problem. But let's make each one of them half a meter. Okay, so our cuts. Cut 1 is for x values between 0 and 0.5. We have the external torque over here. We don't have a value for that yet, but we do have a name for it. We called it TA, so I just have to keep that name and keep the direction. And then we have the internal torque, T. And the moment equation about the x-axis says T plus TA is equal to 0. So the internal torque is negative TA. And that's relevant on the first third of the bar. And then cut 2 is for x values between 0.5 and 1. This one has the force TA at the left and 2,000 Newton meters pointing to the left. And then the internal torque T. And the moment equation about x says TA minus 2,000 plus T is equal to 0. So the internal torque on this piece is 2,000 minus TA. Yep. For which one? So treat that as like a system of equations, or okay, no, you can't do that here because what we're calculating here is a function for the internal torque that only is relevant on that first half a meter. And here we're calculating a function for the torque that's only relevant on the second half meter. And so what we're going to do is use these expressions for the internal torque along with the sum formula for the angle of twist to come up with an expression for the total angle of twist. And once we have that, we know that since it's fixed at both walls, the total angle of twist has to be 0. And so that'll give us our second equation and let us solve for the system. Okay, and then the last cut. This is for x between 1 and 1.5. So we have TA at the left. 2,000, half a meter from the left. And then 4,000, another half meter from there. And then the internal torque T. So the moment equation about the x-axis says TA minus 2,000 minus 4,000, so I'll just combine those. So TA minus 6,000 plus T, bless you, is equal to 0. And so the internal torque on this piece is 6,000 minus TA. And now the expression for the total angle of twist, that's equal to the sum of, I'll write it as the internal torque on piece 1 times the length of piece 1 divided by the shear modulus times the polar moment of inertia. That's all on that first piece. Yeah, that's E over 2 times the quantity 1 plus nu. Yep. And then on the second piece, so that's the angle of twist for that first 0.5 meters. Then add that to the angle of twist in the second 0.5 meters. So torque 2 L2 over G2 I sub P2. And then add that to the angle of twist from the third piece, torque 3 times L3 over G3 times I sub P3. And the sum of these has to be equal to 0 because the fixed joints don't allow rotation. They don't allow rotation of the endpoints. Yep.
So for this to be valid, G and I have to be equal in all three of the ways. So I just do.
Yeah, that's right. So
We could technically leave out the 1, 2, and 3.
well, okay, wait. So they have to be equal in this problem to each other because we don't have numbers for them. So we have to be able to cancel them out.
We got to be constant for that piecewise.
That's right. They have to be piecewise constant to use this formula. But normally, like if they're not the same or you don't know some relationship between them, then you'd have to have numbers for them in order to calculate it.
I've asked you that before. Right?
Yeah, no, that's fine. Okay, so 0, if I rewrite this, so we have negative okay, so negative TA, that's the internal torque on the first piece, times the length of the first piece, divided by G times polar moment of inertia, plus the internal torque on the second piece, 2000 minus TA, times the length of the second piece, divided by G times the polar moment of inertia for the second piece, but that's the same as the first one. Plus the internal torque for the third piece. So that's the quantity 6,000 minus TA times the length 0.5 divided by G I sub P is equal to 0. We can multiply both sides by G I sub P, and these all cancel out. I think that's a movie.
Yeah.
Is that what it is? So you get negative 0.5 TA plus 1,000 minus 0.5 TA plus 3,000 minus 0.5 TA is equal to 0. And we can write this as 1.5 TA is equal to 4,000. And so that is 8/3 thousands. So that's 2666.6 repeating, I think, Newton meters. You can think of this as like the second equation that we got.
Are we going to get anywhere we actually have like a Poisson's ratio for the shear modulus?
Yeah. You'll do some problems like that.
I know just because of,
Yeah. And if it's ever not given and you're dealing with metal, just use 0.3. That's the best guess. And then we can plug back in. Our first equation said that the sum of these two torques is 6,000. So TB has to be 3,333.3 repeating.
what happens if you look at the point on the end? That's going to make it more complicated.
Right. Well, so it depends on the problem. If in this case, this fixed joint was replaced by a pin joint, then you'd be happy because you do your statics and it would be statically determinate and you'd be done. If this was a pin joint and this was a pin joint, this wouldn't really make much sense because that just says that you'd have a torque of 6,000 Newton meters and it would just make this thing spin, you know? So, right, yeah. And so you get an angular acceleration. Any other questions? Yeah. Okay, yes. So I've been doing this sort of a lot with these kind of problems. So let me sort of draw it out more carefully and you can sort of see what's going on. Okay, so here's our whole beam. And over here we have a torque going this way at 2,000. And over here we have a torque of 4,000. And over here, this is a fixed joint, so we have a force vector, RA, and a couple, MA, and a torque, fancy TA. Okay, and same thing over here. So this is RB, couple MB, and then a torque TB. And now go to the statics. So Newton's second law says RAX, RAY, plus RBX, RBY is equal to zeros. So you have two equations here. One says RAX plus RBX is equal to 0. And one says RAY plus RBY is equal to 0. Okay. We don't have enough information yet to know that those are all going to be equal to 0, but you would sort of, if you visualize what's going on here, if all that's happening besides the reactions is a torque here, then it makes sense intuitively that the loads at the walls are going to be equal to 0. Okay. If we wanted to calculate that, we'd have to use a statically indeterminate approach, using first elongation, then deflection, which we haven't done yet, and then the torque. And what we would see is that all of those things I left off will end up being, you can calculate them and they'll be equal to 0. But instead, on these problems where there's no vertical forces, no horizontal forces, we'll just leave those out of there, because that's what it would come out to be anyways. Any other questions about that one? Let's see. Oh. Okay. The next thing we're going to do is deflection. And this is the one where the math is the most complicated. Yeah, exactly. So statically indeterminate structures with deflection. So remember so here's the road map. We did elongation. And that came about two ways: internal tension and also temperature changes. Second is angle of twist. That's due to internal torque. And then the third one is deflection. And that's due to bending moment. You can think of it as due to bending moment and shear force, but since bending moment and shear force have the derivative relationship, just one of those is all we need. So bending moment is what we're going to use. That's the internal bending moment. So let's imagine that we start out with a beam like this. And then after deformation, you have something that looks like this. Okay, and the deflection is just for each x value, how far above or below the original value you are. You might look at this and think, why did there's a big difference in the length of this versus this, right? Why did the length increase in this one? Well, remember that this is an exaggeration. Everything we're doing is small deformations. And if you have small angles, the difference in angles here is small, then an X value in the original, beam is about the same as the X value in the deformed beam. So the only reason that this one is way longer than this one is because I've exaggerated the amount of deformation. Okay. And so like if this is the value X, then this is, actually, let me do it. Let me move it. Just, I don't want to make this confusing. God damn it. Let's see. Maybe there's a smaller eraser. Oh, yeah. Oh, but it doesn't do the. I don't know. I don't have my keyboard open. Oh, okay. Well, too late now. So let's think about it over here. And so if this is X, then this distance here is the deflection V of X. And I wanted to move it over there so that that deflection is a positive value. If you did it here, the deflection is how far above the original position that point is. And so this would have come out as a negative value. Okay. So, and we're going to base this on the theory of elastic beams. These are called Euler-Bernoulli beams, if you want to sound smart. Yeah, Euler-Bernoulli beams. I spent most of my dissertation studying Euler-Bernoulli beams using Euler-Lagrange equations to solve it. Totally unrelated areas. One's just total pure math. One's like physics or whatever. But yeah, that guy was good. And the theory of Euler-Bernoulli beams says that the internal bending moment divided by the Young's modulus times the area moment of inertia is equal to the curvature of the beam. And we're going to denote that kappa, the Greek letter kappa. Okay, so the curvature is defined this way. It's equal to the absolute value of f double prime of x divided by the quantity 1 plus f prime of x, and this f prime of x is squared, and this whole denominator is to the 3/2 power. Okay, so that's the definition of the curvature of a function f of x. So is there an easier way? That doesn't look so great.
Yeah, I'll just.
I know. Me too, and I already have seen this before. Yes, there is. As long as you have small deformations, so as long as the deformations are small, and the beam the angle of the beam never gets that far from horizontal. So let's say it never deviates much from horizontal. Then the curvature is, you can just approximate it as the second derivative of the function. Okay, because what happens is f prime is close to 0 if it stays close to horizontal, and so this stays close to a denominator of 1, and so you just have the second derivative up above.
You're saying stays horizontal? Are you talking about
Yes.
okay.
Yeah, it stays, so it starts out as a horizontal beam, and think of the tangents at any point, you know. So like in the example I did, this crazy example, there are all these places where it's not very close to horizontal, you know, like here, that's really far from horizontal. But we're never going to have big deformations like that.
So if we had a vertical stand beam,
Oh, same idea, yeah, just change your, that's right. Yeah, so essentially it's just not deviating from straight very much.
So that probably changes depending on the length of the beam. Is there like a ratio?
Mm-hmm. Yeah, you're totally right. It totally depends on the length of the beam. I don't know any like rules like that. But it's something you have to consider because forget. Because this equation, this expression for curvature says if you get significant differences from horizontal, this denominator changes, and this just f double prime is not a good approximation anymore. Okay. Okay, so now the expression for an Euler-Bernoulli beam says, so the function that we're looking at instead of f is v, it's the deflection. And so we can say that m over ei, let me move that. Oh. Okay, so this equation becomes m over ei is equal to the second derivative of the deflection. And now solving for the deflection as a function of x, just means solving that differential equation, and it's just two integrals. You know, it's a simple differential equation. Ordinary differential equation, and then matching the boundary conditions. So the boundary conditions are going to come from the behavior that you expect at the joints. So the boundary conditions come from the behavior at the joints. And so here are the joint types that you'll have to deal with. First, if you have a pin or a roller, then, so like if a beam goes over a roller, like, let me draw a picture of it. So there's a pin joint, and over here is a roller. The beam can do all sorts of wacky stuff. Whoops. Not that wacky. There's only, come on. So the only restrictions on what it can do are that the pin keeps it from having any deflection there, and the roller keeps it from having any deflection there. The angles can be whatever. They don't put restrictions on that, but the height at that point we know. So for a pin or a roller, you have V equals 0 at the joint location. And the only other type is a fixed joint. And a fixed joint, it can't move up or down, just like the pin or the roller, but it also can't have, the angle can't change at the fixed joint. So it has to start out horizontal, and then it can do whatever. Okay. But this says that V is equal to 0 and V prime is equal to 0 at the joint location. And the idea is we're going to use these joint restrictions to solve for the constants of integration. Okay, let's see. So let's do this example. Let's say that we have a cantilever at the left. Beam goes out to the right. And there's a distributed load acting on the beam with a magnitude of 10,000 newtons per meter. And we'll say that the Young's modulus is 200 times 10 to the 9th. And the area moment of inertia is 8.3 repeating times 10 to the minus 7. That's meters to the fourth. And we want to calculate the deflection at the right end. So basically, if you put this load on this steel beam, how far down would this point be from its starting position? And the length is 3 meters. So the first thing we have to do is calculate the internal bending moment. So free body diagram of the whole beam. We have a force down at the middle of 30,000 newtons. And then this is a fixed joint, so you have a force vector RA and a couple MR. And I'm going to leave off the torque because there's nothing else producing any torques, so that would just come out to be 0. Newton's second law says RAX, RAY plus 0, negative 30,000 is equal to zeros. And so that reaction force, RA, is 0 for X, positive 30,000 for Y. And then the moment equation says MR, and then the 30,000 Newton force has a moment arm of 1.5 meters. The force is 30,000. And that would produce a clockwise rotation, so that's minus, and that's equal to 0. So MR is equal to 45,000 Newton meters. Okay, so I guess I'll finish this next time. But now that we have the external loads, we're going to do our one cut to come up with the bending moment. And then we're going to use this relationship. So whatever function we get for the bending moment divided by those two constants is going to be equal to our variable, our function double prime. And we'll integrate everything twice and come up with an expression with two constants of integration because we're integrating twice. And those two constants of integration are going to come from the fact that at x equals 0, b has to be equal to 0, and b prime has to be equal to 0. Okay? Any questions? Yeah.
The roller, that could be formed.
Yeah, that's true. But the idea is if this has been designed in any kind of sensible way, you wouldn't have a roller there if the thing is going to be deflected up. So it's the same as when you treat a normal force like you calculate the value of a normal force. If you did your calculation and got a negative value for the normal force, it means that something went wrong with your design or your calculation. It's the same thing here. If you had a roller sitting there and then you calculated a deflection that was up, or it had to be, then something went wrong. Yeah.